So lab 2 was essentially whatever I was discussing, I was showing earlier in the morning. So this is the Flume example. So you can go there, set it up, maybe try to start playing with it and see how it works, and uh, try to do different simulations. I just ran for a couple of steps. Let's see if that is over or still queued. Okay, it's finished. Okay, so if I can just retrieve the data, I think this was something that I was at just ran there. Okay, so it's trying to retrieve maybe. Let's see if it does. Okay. So and this was essentially what Quanchi was speaking about. I mean, I just ran it for 3 steps because we wanted to make sure that we have something by the end of it. So this was what Quanchi and Akash have been talking about since yesterday, and also today he talked about all the what these things mean, what is peak flow acceleration, and all the EDP parameters that you're getting in here. So this is one of the primary post-processing things from the structural point of view. Uh, from the fluid point of view, also you can select. So the most important thing for in order to get the fluid responses and the post processing is we need to go to the event, and in the event it's generally no post processing. So when if you select provide points to get data, you can either extract velocities or pressure, but then you also need to specify what points these need to be. So in the example file, you can find a file called process.csv, which basically gives you a simple tab separated CSV file. So all this is saying is that what is the first column is the x coordinate, second column is the y coordinate or latitude and longitude, and third column is the z coordinate. So this is essentially needed in order to for the fluid in order to get the velocities and pressure at particular points. So you can see that the post processing is extracting the data is reasonably easy. All you need to give is like a, let's say, a file that has the different points that are at which you require this data. And once that can be done, it can be uploaded here and automatically, let's say, right, if you're going to lab 2, just upload the file, and then you just have to send it off to design safe. And then again, already know how to get this data from design safe. You just need to go back to your where is it? Go back to the archive folder, find your job, and there you have the event zip file. So that has the post-processing folder from which you can get all the post-processing data. At the moment, my jobs are still stuck in the queue, which I try to post-process. So you can give it a spin, and if you have any questions, we'll be very happy to help you with it. Uh, the other thing that I just wanted to walk through today with the along with the how to do the post processing was also to uh, show the different things that we have done so far. Second, another thing that is important is to prepare the Stl files. For example, when you go to the project settings, you can also run a simulation as a Stl file. So one of the feature requests that came into us was, hey, if you give the bathymetry data, and can we generate an STL file out of it, and if we can get these STL file back. So if you download the archive folder, you pretty much get the STL files that are generated from any bathymetry. In the lab 4 that is available, I have actually given, so this is essentially you can get as a post-processing out of your simulation as well. So you can find that I've given like a CSV file of a very simple bathymetry. This is reasonably very smooth in the format of x comma y comma z. So latitude, longitude, and some kind of a depth. And its depth is like reasonably very smooth bathymetry in here, just for you to give it a try. And what we can get are these STL files. So you can use this STL file directly in order to generate any simulation and start up a CFD simulation, get it running as well. So let me just put them out there. So I'm just loading all the scripts so we can just. So what the OpenFOAM does is, as we have been talking about so far, it basically creates a box out of everything. So let me open one of these faces. Okay. So this is your bottom surface, which is nothing but our bathymetry. Then we are creating a box inside which we are doing the simulation. So you have an entry, an exit, a left, right, and the bottom and the top, right? So general convention that has been used to when you create an STL file, I think again, this is also there in the documentation. Let me just also open that up in a moment. Uh, okay, so if we go back to that, we go to hydro events and geometry. So if you are looking at the STL file, you can see that we need at least six STL files, right? So entry and exit, right, left, bottom, and the top. And these are the particular names that you have to give to your STL files so that the HydroUQ can parse them and know that this belongs to an entry, this belongs to an exit, and so on, right? And again, like there's again a building. So if you're going to have a building on which you need a response, then the name of this STL file would be buildings.stl. And for anything else, it would be other buildings.stl, which are the other buildings that are around the building which don't have these, on which we are not looking for a response. And one of the most important thing to do when you're preparing your STL file, because there are a lot of softwares out there that will write out this STL file, is that there are two formats. One is the Ascii Stl and one is the binary Stl. So binary STL kind of encodes all the information. So it's probably a little bit smaller and it's kind of encoded in a way you can say. Ascii STL is something that you can easily open in a text file and read through it. For example, let's say if I take this STL file and okay, I have the reader here. I can open it out here and all you will see is a whole bunch of vertices. So basically an STL file is nothing but a triangulated surface. So it has all these triangles that are there. And what is the outer normal to this triangle? So that is what is given, that is defining our geometry. And one of the very important things to do when you submit an STL, give an STL file for the simulation, is also to have your patch name here, bottom. And at the end, uh, let's say if we go back to the end, so end solid bottom. So you want to put these names in there because if you have not given this name, OpenFOAM is not going to recognize the recognize this thing. Well, let's try to see what is happening in here. So let me just go back to design save. I keep going back and forth a little bit. So I hope I'm not confusing you here. I'm just trying to open up an event file and I would like to show you what is happening. Yeah, workspace, data depot. I think I had this, but I deleted this for some reason. Okay. Archive. Let me find a job that is finished. Okay, so we ran this recently. So let me just find. So the name of the job is D565. So D56578. So let me go there. So let me say job D56578. Right. It's slightly a little bit painful to find, but this is an easiest way to find because you can't sort things out in terms of date. That's somehow a disadvantage on the design save that you can't sort it out, but there's an easier way to find them. So let me just open this event files that folder that we had have saved. So like I said, this folder has this zip file has everything that you are doing in the event. So you can find something called a caserun.sh. So this is essentially the script file which is creating all the jobs, doing everything. So for example, here you can see it is combining all your files into a full STL file that is going to be used. And then it does something called a surface feature extract and a snappy hex mesh, right? So when you're doing this surface feature extract and then what it is doing, it is trying to find the sharp edges and all the features that are there in the geometry so that it can kind of build a geometry that is conforming to your, build a mesh that is conforming to the geometry. But then when you do a snappy hex mesh, it is going to look for, so let's open our snappy hex mesh dictionary as well. So here we have the snappy hex mesh dictionary as well in the file. So you can see that it is looking for these HDL files, so entry, exit, top, bottom, left, right, building, full, right? So it is looking for these HDL files and it is trying to see if it can find these tri-surface mesh, right? And unfortunately, when it's not able to find it, then it is going to give you an error. So if you're going to use an STL file, then you need to make sure that you're firstly given the STL files with these particular names, and secondly that it is in ASCII format. And when you're giving it in ASCII format, most of these writers will not add the name at the end of it. It'll just leave it as end solid and at the start as start solid, right? So if you go back to the start, it is just going to give it a solid and leave it there. But we want to make sure that we add it as add our patch name in there that we have given end and at the both the places, so that it can be ensured that the snappy hex mesh is able to recognize what is the patch name of this STL file, right? So essentially, if you look at it, each of these are a single patch. So let me just close them and we can see. So if I put the bottom, this is just a bottom surface. It's just like a one single surface. It's not a full 3D mesh. It's just one surface mesh. So it's kind of like a 2D surface. And then if you look at the entry, so there's another STL file. So which is so only caveat is that all the STL files together should still form a watertight geometry, and that is one problem. So when you write an STL file, you need to be careful that the files you're giving forms a watertight geometry. If it does, often with STL files there can be gaps and things when this should not happen, and this need to be taken care of. So that is where if you, for example, use the HydroUQ to give the bathymetry, it's automatically going to generate. So this is the bathymetry generated, the STL file of this bathymetry is generated from the HydroUQ, right? So you can see the exit, and then you have a patch for the left, and then you have a patch for the right, and then you have something for the top, right? So these are the 6 patches. It's going to combine this and going to mesh this thing. So that forms our total geometry that is going to be meshed. Now, if you have put a building in there, then the building needs to be in there, and you need to make sure that the right names and patches are given in there. This is a very critical thing. And if this is not there, then you will not get a mesh, which automatically, let's say, negates the rest of the process that is there with it, right? So most important thing is to ensure that so this is available in the lab 4. So I've given a CSV file and generated STL files that are there. That is just for you to play with and try to see if you can generate these STL files yourself, right? But that apart, I would also like to go back to lab 1. This is something that we were supposed to discuss a little bit in detail yesterday, and was probably a exercise for you to try out. But we did get a chance to discuss in detail, I think. Yeah. So the same file is also given. I've also given the same file in this lab 1 as well. So let's look at the lab 1 in detail, so that this kind of gives you how to prepare all the files for your simulations, right? So that's the most important thing when it comes to preparing a bathymetry and things like that, right? So here what we have is a simple geoclass simulation, and we have the solution files, for example, 4.q and 4.t. Uh, and if we look at these files, right? So let's just open the file. 4.t has, as I think we went through this in a detail yesterday, has the time information and the number of grids and the number of dimensions. These are most important to us. We already know it's a 2D shallow water solver. So it's you have the X and Y dimension, and you also have a number of grids. So if we looked at this again yesterday, so if you open the 4.q file of the output from the geoclaw, it basically has a grid number here, right? So when we say the 4.t. Okay, so yeah, so the T003 would correspond to Q003. So we just need to be careful on that. So essentially it says it has 9 grids. So you have a grid number here. So now let me, if I just try to do a find, right? So you can see that I'm able to find 9 grids. So they're essentially 8, 6, 3, 5, 2, 7. So essentially you can see that there's grids from 1 to 9 available out there. And so each of these grids have these a number of mx and my are a number of them in the x direction, number of cells in the y direction, and what is the x low and y low, dx, dy. We discussed all of these yesterday in our point, and the lowermost point, and the distance and x direction, distance in the y direction between the points, and number of points in the x and y direction, right? So we discussed all of these yesterday. So our goal was to basically take the geoclaw outputs and input into the open form, or into open form, and that's what HydroUQ is doing. So I wanted to a little bit demystify the process as to what is happening in there. So that is what essentially is there in lab 1. Let me just share this window so that it's a little more clear. Okay, so let's go there. Right. So if you go to the lab one of the HydroUQ repository, you will be able to find that you'll find this uh, Jupyter notebook that is there. So let me just again share the GitHub repo address for anybody who has joined in newly. Uh, right. Right. Yeah. So this you can have a look at it. So that's how I just wanted to demystify the process of what we are doing with the shallow water solutions and what are we constructing from there, right? So what is happening in here? I'll leave this. This was meant to be like an exercise. I'll just go through it in quick detail, and you can probably just go there. And it's very easy to run a Jupyter notebook. You can just press Shift Enter, and it'll run each of the cell. You just press Shift Enter for each of the cell. Or if you don't have a Jupyter notebook installed, there's something called a Google Colab. So most of you might have heard of it, but just for others, you can go to Google Colab and so you can just upload this Jupyter notebook into the Google Colab, and you should be able to use it. So it's just like Google Drive for Jupyter notebooks, you can say, right? So there are a couple of other things as well, like Binder and things. Also, you can use the Google Jupyter notebooks on Design Safe, and Design Safe likes Jupyter notebooks quite a lot. But these are other alternatives that are also there. So probably Google Colab and things like that, which so, right. So essentially, what am I doing here? So I'm basically, firstly, let me go down here. So I'm giving a path to a folder called GeoClaw. So if I go to the lab one here, you can see that I have a folder called GeoClaw in which I have all the 4.q and 4.t files. So I just put 10 of them because it can take a lot of time to process. And like we were talking yesterday, we need to be wary about how much time are we simulating and what is our domain size. Because if our domain is too small, and we are trying to simulate for a long time, then the shallow water solver boundary condition is only one way. So you will have the reflection, which will make it unphysical, right? So we need to be careful. And secondly, also in terms of basically for the time, I have just taken 10 of these files, but you can find all the 80 frames of the Hurricane Ike here. So I've also given the zip file with all the 80 frames of the Hurricane Ike. So this was a simulation done with GeoClaw by my student, RU student, and she's done some amazing work here. And so I've just taken one of the examples of what she has ran. And so you can go back and look at this GeoClaw folder, which has all the details. And we are trying to give a path to it, and we are trying to get two vectors out of it, right? So if we look back at our this 4.q file, so let's see 1 of the 4.q file. So maybe I can maybe take something else so that it'll first one will probably be just zeros, just to avoid all the zeros. So you can see that there are 4 columns coming in here. Okay. And there is also some information here that is stored, which is basically the store information about the grid. Or in other words, this is the information about the X and Y. And we also have some information about the time here, right? So if we go to the 4 to dot T, or let's say T dot something, let's say T dot 4, we have the information about time. So at every X, Y, Z, X, Y, and T, we have some 4 outputs that are coming out, right? So we need to, so one question is, what are these 4 outputs that we are getting in here? So these 4 outputs are nothing but, you can see here, I have given it, our inputs are X, Y, and time, which is the XY grid because it's a 2D grid. And at each point we have something running in time. Our outputs are H, X momentum, Y momentum, and eta. H is nothing but the depth of the water at that particular X comma Y, right? Your bathymetry is constant, right? Your ground is constant, but at the end of the day, your water level is not the same at every X comma Y, right? Or even at the same X comma Y, it's changing with time. So there's a dH by dt and also dH by dx. So it's also varying with spatially and in time, right? So this time is one of our outputs. Our second output is X momentum and third is Y momentum. So this is nothing but our H into U bar. U bar is our average velocity into H into V bar, which is our average velocity in the Y direction, right? So you have X and Y. So you don't have the U and V itself, like in our full Navier-Stokes, but you have the U bar and V bar. U bar is nothing but the integral of U into dz, integral of U over the entire depth of the water. Now, but then the depth of the water itself is changing, right? So so we need to be careful about that. And last one is eta. Eta is nothing but our bathymetry plus H. So you can say, okay, why do I need to output it? It's H is one of our outputs, most important outputs, from where we're also calculating what is the eta. In other words, eta is nothing but the let's say position of the free surface of the water. So we have the bathymetry, over that we have the H, height of water. So eta gives us somewhat the free surface position at each x comma y. So right. So from H you can always H eta minus H will always give you the bathymetry of the ocean floor, right? So that's something important to keep in mind. So what we are going to do is we are going to run a small script here, which is essentially like all these things. If you can have a look at them, I would leave it to you. So this is doing nothing but it's passing this Q file and the T file and putting everything into a NumPy array. So essentially, like you have the X and Y, everything is being written into X and Y. X has all the inputs, that is the X coordinate, Y coordinate, and time, right? So, and probably time can be the same for a lot of them. For example, here you can see first few of them are the same because, for the same time and different X and Y, you're getting all the data there. And then the Y has all the H, X momentum, Y momentum, and the eta, right? So we have, once we have this information, now we can easily calculate our bathymetry. So if you want to, you need two things from this simulation, right? So you need two things from your shallow water solver into your CFD. One is what is the geometry. So once I have the geometry, I can mesh it, right? So I need the X comma Y comma Z at every point. So I can create some kind of a point cloud. And from this point cloud, I can create all this box that I was showing, right? So our bathymetry is this bottom thing. Our box is the sides and the top and everything, which will, create as a closed box. So we can do this external flow, around the building. So first thing I'll do is I'm just combining them and I'm basically copying it to another thing. And then I'm trying to extract my bathymetry, which is nothing but the eta minus H, right? So if you look at it, once I have combined this, so my index, you need to be careful for those who are coming from MATLAB, that the index here again starts from 0 rather than 1, right? So my index is 0 and 1 and 2 are nothing but X, Y, and time. Then 3, 4, 5, 6 are H, X momentum, Y momentum, and eta, right? So now I am doing a 6 minus 3, which is nothing but I'm just, instead of storing eta, I'm storing what is the bathymetry of the ocean floor. Because I want the X, Y, and Z in order to reconstruct my geometry, right? First thing, so I have now somehow in my XYZ array, I have all of these X, Y, and Z coordinate. It's probably not one beside the other, but I have this information there. Second thing that I want, if you remember, when we did in what we did when we were looking at it yesterday, is we said that we have this huge domain over the Pacific. If you remember this Google Earth simulation that I was showing, you had this earthquake at Alaska, and then there was a wave propagating all the way to Crescent City, California, and Honolulu in Hawaii, and so on, right? So you had this huge domain on which we cannot do a CFD. So we said we want to choose a smaller domain. So what did we do? We said we'll create an interface. So if we go back to our documentation, I'll keep going back to the documentation so that I can help you relate to it. So we said we create a very small file that says entry, exit, right, and left. And what are the 2 points that make the entry, 2 points making the exit, 2 points making the right, and 2 points making the left, right? So that way we have this square out of which we can cut out of the bigger geometry. And from there we get our subdomain, right? So that is our subdomain on which we want to do this simulation. So second thing that we now that we have the entire bigger domain, what we are going to do is we are going to try to get that small subdomain, right? So that is what we are doing here. We are trying to read the interface file, which is nothing but interface.csv, and I'm trying to get my subdomain. So I'm trying to get the points of the exit, entry, and everything. And I'm also trying to find what is the X max, Y max, X Y min, X max, Y max, and X min and Y min. So that basically I can use in order to cut down my full bigger domain into a smaller subdomain, right? So once I do that, I create some kind of a tolerance. You get this tolerance is like, let's say, you can probably say 10 to the power minus 2, or I am probably using some distance in here, but some kind of a tolerance. And I try to find all the points that are there inside this subdomain. So once I have all the points inside the subdomain, I can create some kind of a, so now if I look at it, what is the max? I had my entire domain was essentially between minus 70 to minus 99-degree latitude. And on the, it was on the longitude side, it was between 3 degrees to 27.5 degrees, right? So now I have extracted something here. I can probably try to see what is the, let's say, we can also try to see what is it for our interface as well. We already have, okay, we already, that's the input that we are giving, so we don't need to do that, right? So so once we have this, we have all our X, Y, and Z data for the particular bathymetry that we need, right? So we have the bigger bathymetry from our shallow water domain. From that, we cut down into the points that are there inside our interface. And now we are going to use these points that are there in our interface in order to get our bathymetry. So that's what I'm doing here. I'm trying to use this information in order to create a small Stl file for my bottom. And similarly, I'm going to use this same thing again and again to create the entry. And similarly, you can use the same code to create the exit left and right and top and any building patches in there. I'm giving you all this code because I want to try to demystify how are we going from the shallow water to the CFD? What are the things that we are doing in there? Just so that we understand that and we can use this tool with more confidence in there, right? So you can, I've left this out so that because it's just a repetitive code, or you can also call it in a loop for different patches, do the same thing. So that is what is done in the actual code. Here I will separately written them out so that you can understand what is happening, and just to try to make the code, maybe it's a little more elaborate in the Jupyter notebooks so that it's easier to read and understand. So once you have these, you also have the U average and the V average, right? So we already have the H, H into U bar and H into V bar are already there in our solutions. I can use this, and I also know the H at every point, right? So which is the depth of the water. If the depth of the water is less than zero, so again, I'm defining some very small tolerance, 10 to the power minus 12, because since these are floating point numbers, I cannot say if it's equal to zero. So I say if the absolute value of it is less than the tolerance, then I would say that the U average and the V average are zero. So if H is zero, then pretty much H into U bar should also be zero, right? If it's not zero, then probably there's something going wrong in there. If it is less, if it's equal, H is zero, then U bar is also zero, V bar is also zero. If it is not zero, then I divide by H in order to get my average U and average V velocities. So basically from there, once I have these, I can plug them into my equation in the slide number 29. Let's go back to that here. I'm trying to relate to all the materials that you have access to so that you can go back and give it a try and see how it compares with whatever you would have. So let's go to slide number 29, that is here, right? So essentially we can say that our friction velocity, I mean, see something approximately equal is between 0.05 of the averaged velocity minus or to 0.1 of the average velocity. So it's left to you. You can take one of these numbers that gives you a reasonably accommodating answer. So that kind of gives you the U star of 3D. Kappa is your von Karman constant 0.41. And then essentially what you have is H2D, which is nothing but we already have it in our information. We have the H. And we just need to be careful to say that if H is zero, don't divide by there, because H is zero, then it's pretty much zero. Be careful about that. And then what is the Z? So Z is essentially the depth from the maximum topography to zero height. So we can get the Z. That would essentially give us the 3D reconstruction with 3D velocity, both in the U and V direction. So there's just the equation you can plug in. So I just left that as a last exercise for you to give it a try and try it out and maybe plot out how you're what the solution that you're getting in there for each time step, right? So this is essentially if you have any questions, I would be very happy to answer. But this is essentially just a glimpse of what is happening in between when we convert our shallow water solutions into a 3D CFD solution, going from a 2D into a 3D. Of course, this method is not the only method to do it. So so this is essentially kind of giving you an idea of what can be done. So if you go to a researcher guide, you can see that you can create your own CFD. So I converted my 2D velocities into a 3D velocity. I pretty much have given you here the code to go get your shallow water solutions and get all the information, and also to get convert it into 3D. But you can, instead of my equation, you can probably plug in your own equation. So once you have your own equation, you pretty much have this entire template filled up in there. So you can come to us and say, hey, I have my own way of doing the shallow water to CFD. Can I use the HydroUQ? So then we will. So you then you'll be able to plug in your own Python code and use it as a research tool to run different research problems, explore different methodologies of how do you go from shallow water to CFD and so on and so forth, right? So this is just one particular idea. Similarly, you can also, for example, if you're a numerical person or if you're using a different solver, this could be like a solver that you have been using in your group, or let's say you don't like to use OpenFOAM, but you want to use something else. You can just come to us, and again, there's a template that can be easily filled up. And if you fill this template up, you just can easily use your solver instead of the OpenFOAM solver. So it's a kind of a plug and play. Or for example, if you're using a different wave flume, so you can just come and just let us know, and we can help you with creating these researcher modules. So HydroUQ need not necessarily be just like something that is fixed, but you can bring your own modules. For example, like now people have their own user elements and user materials when it goes in, when they use softwares like Abacus or Ansys or things like that. So this is something like you can think of this is like your user element for HydroUQ. You can bring in your own ways of doing things rather than having to follow a preset pattern that is available there. There's a template code for everything, very easy to write, and we would be very happy if you are interested in writing one of these codes or scripts to use your methods instead of the HydroUQ methods, right? So that is a general outline of what is happening between the 2D shallow water solver and between the 3D solver, 3D solutions or CFD itself as a boundary condition. So just to wrap up the session, I think we are pretty much at the end of it. In the last couple of days, we looked at how to use the HydroUQ tool. So we learned how to load a job, how to save a job, how to submit a job to TAC, and how to monitor it. And we also looked at how do we go to design safe and get our fluids results. How do we look at the structural results from the HydroUQ? You can look at go back to the repo that I've just shared. So there are 4 examples out there. So the lab 4 is essentially all the Stl files that are there. So you can go put this thing into HydroUQ as a Stl simulation, as a simulation using Stl files. You can set up the boundary conditions and give it a try. And I think that would be the best way for you to explore the tool. And if you're stuck anywhere, we are very, very happy to help you with it. You also have our email. You can just shoot an email and we would be happy to help you with how to go about it. Just so and I think also we went over how to prepare the Stl files. Just make sure that it's in ASCII format, and most important thing is the name of the file, and the name of it, the patch is there in the bottom and the top, and that's the name of the file as well. That's the most important thing that can be often very easily missed, and then we might be stuck to see why the simulations are not running, right? So a lot of this information is there already in the user guide, but we would be very happy to help you with it and help sit with you and try to make sure that your simulations are running. I think there was a question in the last session about the bathymetry data download. There's a website from GEPCO. I think Kyle shared the link from where you can give the boundaries and you can extract it as well. If you go back here, essentially you can also download the data as a netcdf file. I think this is also something that we are looking at to see if we can add it into our tools where along with the topography data that is already there, we can also have the bathymetry data. So you can just give this information and extract the bathymetry from there rather than having to even bring it into the tool itself. Uh, right. So yeah, so I think we are pretty much at the end of it, and we have probably covered most of the things that were planned. And again, for the post processing, it's really simple. You just have to give a set of coordinates. You want the velocities and pressure set, and you're able to extract the information from there. And if you have any questions, we are here to help you with it, and I would be glad to answer them.